So, hi, this is Dave McComb from Semantic Arts. We're at the GIST Council, June 8th, 2017, and today we're going to talk about a topic that comes up over and over again called what we call optional properties, or how do you declare that something is optional in an ontology? And we've with GIST and with all of us, we've gone through many different ways of doing this and thinking about it. It's kind of a rich topic, and we're going to kind of recreate some of our history and things like that. But as soon as you get into it, you recognize it's a little bit more than just optionality. It sort of bleeds into a whole bunch of other stuff that we're going to get into. It's really, once you leave traditional design behind and get in semantic design, this idea that we used to have of just putting properties on classes, as we used to do in relational and object design, we kind of have to leave that behind. And how that shows up is how do you suggest that a property could be used without insisting on it. But there's something deeper behind that yet. When Tim Berners-Lee created the semantic web, one of the things he famously said was, on the semantic web, anyone can say anything about anything. And in what I like to say is life imitating art. I think Tim Berners-Lee was pretty prescient when he said that. These days anybody can say anything about anything. Speaking of Tim Berners-Lee's predictions, we were interviewing him once and asked him, this World Wide Web thing turned out pretty good. When you were inventing it, is there anything that happened that kind of surprised you, that you didn't expect? And he said, yeah, I didn't expect the cat videos. Anyway, this whole anyone can say anything about anything is part of what they call the open world assumption. And one way of thinking about or talking about the open world assumption is to say that any statement, any assertion, any triple that you could possibly say is satisfiably true. That's some of the technology they use in the web. Anything is possibly true except things that are provably false. Things that are provably false are not possible. If we kind of restate that a little bit and complete it a bit, any information you have in any repository or database is incomplete. And you have to reason with this incomplete information, and reason in such a way that if you were to come across some additional valid information that's still consistent with anything, any other information you come across is consistent unless it's logically inconsistent. That isn't much less tortured than the previous one, but and when you do finally come across something that's inconsistent, the real issue, as we'll get into here in a minute, is, was the new information wrong, or was there something that you already thought you knew that was wrong? This is essentially just how description logics work. Now, this is where the flexibility comes from, and what we've been touting so much these last several years is how great flexibility is. But of course, flexibility comes at a price. And normally, the price you pay for flexibility is you get more overhead or indirection or abstractness or pointing at pointers to tables to pointers and all that kind of stuff. But in this case, the flexibility doesn't really cost you very much. When you sit there and study this and look at how the triples are and how the graph is, it's certainly not a performance penalty. If there's a price, it's that when you stare at a data set that's that flexible, it's kind of hard to predict what you're going to find. And that makes it harder to write programs and all kinds of things like that. So that's where this whole thing comes from. To make that less abstract and more concrete, there's an example I've been using a lot lately because I just kind of like it. We've got a database table with information about secret agents in it. It's classic relational. And in a traditional system, anyone can't say anything about anything. Anybody can only say things if the tables and columns allow them to say it. In this particular little tiny database, you can only talk about names of our agents, because that's all they've got, last names and full names. But if we took that data and turned it into a graph, turned it into triples, we'd have at least one triple there that looks like this: agent. That's a little short name for the namesake. Agent 007's full name is James Bond. And once we have that as a triple, we can easily add any other triples to it, which is handy. If you go out there and find more stuff about 007, you can just attach it to it. Anything you might say about James Bond, for instance, you might have a martini preference. There's a little martini preference object, and you can want it stirred and not shaken. What you can't say, this kind of bums me out. I went back into DP recently. I used to do some examples with roller coasters, and they had vertical drop on the roller coasters. Now they don't, which bums me out. But anyway, imagine we went into DDP, found vertical drop, which was a property that had a domain of roller coaster, and if we happened to know that James Bond was a person, and persons were disjointed with roller coasters and all that kind of stuff, this assertion would break our model. And it'd probably be a pretty good idea to try and keep an assertion like that out of your triple store if it is going to break your model. So what this is saying is all we're really precluded from saying is anything that's logically inconsistent. At first I was thinking we've got a basket of terms, our properties and classes and stuff, and that's our vocabulary of things we can say. But really, we can make an assertion with a property we were previously unaware of. If I go find a property from DBP and want to make an assertion using that property against data I already have, we can certainly do that. So to kind of restate where we started here, something being optional isn't the problem we have here, because almost everything is optional. I'm going to make the case that everything other than that which is precluded is optional, which is, different. The reason we even think about this problem this way is we've been doing object-oriented and relational for so long, because in those things, in order for something to even become optional, you first have to put the property on the class and then say whether it's optional. In other words, going back to the martini thing, you can't even talk about optionality until you put the preference on the table, and then you can say either, no, it's required, everybody has to have a martini preference, or it's optional. So in our world, optionality, like the Buddhists say, isn't the moon, it's the finger pointing at the moon. We're going to say optionality is a finger pointing at where a real problem is. What we really have a problem with is we don't have a way of even saying that things are required. So if you don't have a way of saying that things are required, you struggle to say whether things are optional. And we also don't have a way of saying that something is suggested. In fact, that's really what we're going to come back around to in this presentation. But while we're at it, we don't have any good ways of saying what's prohibited. So we got three things here. We don't have a very good way, and we all, because we've been building applications now for a long time, we've all sort of finessed this a little bit, but that's it. We've sort of finessed it. We don't actually have a consistent way of dealing with this. So what have we got in our bag of tricks in ontology land for dealing with those? Basically, we got restrictions and domains and ranges. That's our main bits of ammo here that we're going to go through. And in the world of restrictions, we have, there are 7 or 8 types. There's the min value, max value, sum value, all that. But really, we're more interested in this conversation in the distinction between the restrictions that are necessary, well, we'll get into this, and those that are sufficient. And obviously, necessary and sufficient is a combination of both of those. So necessary restriction, here's a graphic way I've been drawing these things lately. We've got a property. We say if having a birthday has some values from a time instant. That's a way of describing a restriction in OWL. If we then said that a person is a subclass of that restriction, so in Protege, if you say, if you're on the person class and you say there's a subclass of the has birthday some values time instant, that's a way of saying that's necessarily true of all persons. So if you're a person, we know that you necessarily must have a birthday that is some instant in time. Really, in semantics, that's saying in the real world, we know this to be true, and so therefore we wouldn't be surprised if we came across a birthday for a person. In fact, we would expect it. This is true in the real world that people do have birthdays, but there's nothing about that in any particular system that makes it either required, optional, suggested, certainly not prohibited, you would hope. But the truth is, most information systems aren't interested in birthdays. You know, if we said that we know that people have birthdays, and therefore birthday is required, then every time you try to use GIST in a system, we insist that you put people's birthdays in, and pretty soon you quit using it. So it looks like it implies required, but it obviously can't from any practical standpoint. Let's go the other way around. Let's look at what is a sufficient restriction bias. This is an example from our class we like to use. If we said our restriction is if you have this credential, it's a U.S. passport, then that's good enough to infer you into the class of all U.S. citizens. That's inferring into a class. The other one was if you knew you were in the class, inferring your property. So, you know, if Dave has this credential that happens to be a passport, then I can infer that I'm in that class. But that didn't help us very much on the required, suggested, prohibited front. Because if I require that I have the passport, then there's no point in my screwing around with the inference here. I mean, the whole point was to have Dave, you know, and have the system figured out rather than making it being required at input time. So that one's not a very good candidate. Let's go over to domains and ranges, because a lot of tool vendors have gone down this path and said things like, you know, if I have the property, and if I say when I created the property that the domain is U.S. citizen, then I know to put that property on any form that deals with U.S. citizens and, you know, ask them about their credentials. And now we got a couple of interesting problems. And by the way, this works the same for range, but I'm just going to go through the domain example. The first problem we have here is that infers me into the class of citizen regardless of what my credential is. It doesn't have to be a U.S. passport. It could be anything. So in fact, that's just wrong. That wasn't helping the problem. And so people who use this approach have a tendency to say, oh yeah, I have to make a more specific property. Now having a U.S. passport is the property that's associated with U.S. citizenship, and it's maybe a sub-property of credential, which now I have to make up a new class called credentialed person or something. This line of thinking sort of works, but it encourages a kind of a behavior that we're trying to prevent. And the behavior is you just keep adding properties. You know, if you really want to go down this route, you end up creating a new property every time you create a new class, other than the ones that are directly inherited. So you end up with not very much property reuse, which we think is a problem. So given that I've just set everything up and knocked it all down, we sort of don't have a solution. Not that we don't have a solution. We've been doing this for years now, but I'm gonna suggest that the ontology isn't the right tool for defining any of these three things, but I'm going to give it a go here in the next couple of slides. But I'm going to suggest the reason it isn't is because those things are application level concepts and not mean, certainly not shared meaning kinds of concepts. So let's kind
Dave?
of work. Yeah.
Can I, a question of clarification. Can you go back to that previous slide? So when you say the ontology is not the right tool for saying required, I'm wondering if you could clarify, because if you have a necessary restriction, then that does mean it's required in the world. Now, do you mean
required in the world? Yeah, not in an information system.
So you mean when you're talking about required, suggested, prohibited, you're specifically talking about the database of triples?
Yeah.
Okay, just wanted to be clear. Thanks.
Mm-hmm. Yep. Yeah. Actually, yeah, that's literally true. What we're, in fact, I'm going to go. Yeah, that's a good intro. We're going to go a little deeper into each of those because this is semantics after all. What do I even mean by required, suggested, and prohibited? What I mean by that is in an information system, if you say that a property or a property with a conforming object on the end of it, if we say that's required, that's equivalent of saying I would rather throw away new information that doesn't conform than to accept partial information. And that's what, in the traditional database system or object-oriented, anything like that, when they say that a piece of data is required, this is literally what they're saying. Somebody fills in a form, they hit submit, and it bounces back and says, nope, you have to fill in the into go down price field. And so nothing gets persisted, and it just sits there and won't accept new information until you fill out all the things that are required. So yeah, that is what I'm meaning here. The idea of suggested sounds like optional, but and in a traditional system, suggested and optional are pretty much the same. But here, because almost all properties are optional, what we're really talking about is hinting, and the hint is either to somebody who's designing a user interface or somebody who's designing an API, a programming interface. It's a hint about what fields to put into the view of the message, because you could put every field in the ontology in an API, but that is kind of not helpful. And then, once you put the field on the form, you either allow somebody to supply a value, or if it's suggested and not required, you say it's okay if you don't give me a value. It was just a suggestion. And keep in mind, in this thing here, whoever's designing the interface, user interface or the API, could be a human or could be a software program. In other words, model-driven development is where the software program is picking up the hints and designing the system. And then finally, the idea that something is prohibited is saying if you attempt to add this triple, the system should reject it. In other words, I would rather not have this information. I consider this to be anti-information. Keep it out of my system, out of my triple store, because it has negative value. Once you add it, my whole thing becomes inconsistent, and I can't do any reasoning, and I'm worse off than I was before I had this piece of contrary information. So one kind of prohibited is exactly that, things that make the ontology inconsistent. That's not the only thing, though. Well, yeah, perhaps you might say I want to have a limit on cardinality. You could have a system where we said that people can only have one spouse, and you could prohibit the addition of the second one. The semantic approach is to create a class called bigamist, and when you find the second spouse, you put the person in the bigamist category. But you could certainly imagine scenarios where you want to prohibit things on a cardinality basis, or we should be able to define any arbitrary exclusion. If you have a project management system, as we do, and you allow vacations to go into it, maybe we want to say, oh yeah, make sure you don't put a budget on vacation, because that's not what we're doing here. So if that's what required, suggested, and prohibited means, let's take a look at how some of our common approaches that we've tried over the years satisfy them. Start with domains and ranges. Then we're going to do necessary restriction. We're going to try the min zero thing. We're going to look at annotations, see how all of those kind of stack up. If you're going to go this domain and range route, and I know some people have, you can add properties to subclasses, and then so any one class will have the suggestion is the set of all properties that have me as its domain or any of my superclasses as its domain. So if you do that, you get the equivalent of object-oriented. You put a prompt, every time you want another property on another class, you go create another property. Also, if you do this is mostly about suggesting. It doesn't really have that I can figure out a mechanism to separate the required stuff from the suggested stuff. Let's try see where we get with necessary restrictions. We could declare anytime there's a necessary restriction that is required, because that's logically true. That's the birthday example. But to say that therefore is required is to say if we don't have it, if I don't get something I know to be true in the world, then I don't want any information about that person. So if we go that route, you end up having to design your ontology such that the only properties you're willing to put into the necessary restrictions are those that you're willing to enforce. And in this realm, there's not a good suggested option. That's where our friend min0 comes in. If you have a cardinality of 0 in semantics, that means you must have at least 0 instances of this. So, one of the good bits of good news is that a min0 restriction has no effect on inference, so therefore you can put it on with impunity, and it can be a hint to a developer. So when they look at it, they see the min0 and they go, oh yeah, I should probably put that on the form or whatever. It could even be what we call a pragma, which is something if you're writing code to generate the UI, you could say in the code, anytime you find a min0, put that field on the form. So, this is a way of suggesting stuff. It's not really a way of requiring things, but if you said the necessary ones are required and min0 is suggested, you get kind of a solution here. But if we're talking about pragmas, one other approach that's been used a little bit is to say let's do this with annotations. So recall the bidding here, an annotation is an assertion that the inference engine ignores. Pretty much what an annotation is. We mostly think of them as comments because most of the annotations we use most of the time are literal strings that we put on things. RDFS label, RDFS comment, some of the other pref label, pref label, alt label, all these kinds of things are the equivalent of a comment in code. So, we could have U235 has a label, it's Uranium 235. But you can connect annotations and use it like an object property. We can connect to URIs with what looks like an object property, but really it's an annotation. And you can do that if you want to avoid inference. Because in some cases, if we want to put an annotation between U235 and uranium, it's an isotope of that. If we did that, that would not cause, that light blue there indicates it's an annotation, that would not cause any inference. Now, why do you want to avoid inference? I mean, there's several reasons you might want to, but one of them is anytime you end up working in the metadata land, inference is totally going to get in your way. So for instance, if you wanted to say on the class U.S. citizen that having a credential is a required field, you could create an annotation and it wouldn't run any inference on that. if it did run an instance on that, you'd have a problem. So in some ways, this might be the best ontology-centric way to take care of required, suggested, and prohibited, because you just, you could create special annotations for those, and you go from the class to the property. It's not going to break anything. The only downside is it's a little hard to then qualify what kind of object has to be in the triple. So you could, from the class, point to the property, but it's not a good mechanism here to go that one step further, what we like to do with the restrictions, which is, say, what the filter class is. So the overall on you doing required, suggested, prohibited in the ontology is most of these things tend to, in my opinion, put more application design in the ontology. And if the ontology is an application-specific ontology, maybe that's not such a negative, because if the ontology is for a particular application, putting application logic in it is not as much of a negative. But if you're trying to use the ontology for integration, the more application-specific stuff you put in it, it's kind of clogs it up for its integration task. And that's where we come to SHACL, shape constraint language. It's almost a standard. It's trying to get out of committee right now. And it's mostly about declaring constraints. It uses an ontology. Some people have talked about using SHACL instead of OWL, but actually that doesn't make much sense. SHACL needs a vocabulary. It refers to the classes and properties that are defined in OWL, or at least RDFS. And we think OWL is a good language for defining meaning. So coupling it with SHACL gives you meaning and then constraint on top of it. So seems like an excellent marriage. SHACL came from this thing called SHEX, the shape expression language. And SHEX was syntactically more compact. It does the same thing, more or less. Actually, SHACL does more than SHEX did, but I kind of like the way SHEX rendered things, and certainly in PowerPoint, it's way more compact, so it saves some real estate. So this is an example of a SHEX shape. This would be the employee shape. You have to declare what type of thing this shape is about, and then you declare what properties and what their filter or what their object has to be. And in this case, the absence of a little symbol on the end of that just name line says to SHEX that there must be exactly one name, and it must be a string. And then the last line there, the reports to line, says that they have to report to something that is also an employee, therefore conforms to this employee shape. And they can either report to 0 or 1. That little question mark is shorthand for 0 or 1. So they have these little symbolic ways of dealing with cardinality constraints. What was really cool about this, this didn't even trip to me until I was putting these slides together, and I literally accidentally put them in this order. But those last two, the plus sign and the blank, literally means required. It means if you try and submit triples that don't have, in this case, a gist name, then we'll reject it because it was required. The first two, anything that has 0 or more, are literally optional. So if you didn't put them in, we wouldn't care. We'd let you go. SHEX didn't have this, but SHACL does. This idea that you could declare that you can have a maximum of 0 of this type of triple, and that's just a way of saying that that type of triple is prohibited in this shape or in this class. And then if you put those top 4 together, that is what's suggested for this class. In other words, if I put blank, question mark, asterisk, or plus, I'm suggesting pretty strongly that anytime you're creating instance of this type, that these are the properties you're going to put on it. So here's how Shex and Shackle relate to your ontology. In this case, I happen to make up we have a semantic arts ontology that extends GIST. So the type was semantic arts employee. We use name from GIST. We have a reports to property also from that ontology. So you can sort of see how this thing ties into an ontology. And the spec is a little quiet on this particular topic, but our plan is that Shackle be bound to a particular repository. So, and typically a repository has the T-box, has the ontology in it. So we would say in this particular repo, here's the rules about what we're going to require, suggest, and prohibit, so that anything in that repo conforms to that shape. But what's kind of cool is you can have another repo that uses the same ontology, uses GIST and semantic arts, and over there we could say we're interested in different things in this repo. This one has, maybe this is for payroll or something. You have to have a billing rate, a pay rate, and start date, and you know, all that usual kind of stuff. So now you've got some information in one repo for one purpose, some in another repo for another purpose. You can pretty much guarantee what you can do with either one. We know if we execute a query about either one, what to expect. But we could also federate a query across both of them because the meaning is identical. We not only is the meaning of what it is to be an employee identical, and the employees should have the identical URIs, but also the meaning of every one of those properties. It means the same thing. The repo on the right knows what it means to have a name, even though they didn't insist on using it. And in fact, if we went out and got some open data that conformed to this, we could have a whole bunch of data that wasn't constrained that we could combine with these two data sets. So, kind of sum it up. I think the issue around optionality is that for 40 years or more, we've been designing relational and object data systems and databases, and we've been putting properties on classes, and that whole mentality has kind of led to us thinking about things as whether they're optional or required. But it's this whole putting property on classes that makes things complicated and expensive. So if we can, separate meaning from structure, I think we can reverse that trend. But just because we can separate meaning from structure doesn't mean that sometimes we need some way to put a little bit more structure on it. And in particular, I think this idea that things are either required, suggested, or prohibited is the structural thing we're looking for. And there are some techniques that you could do that in the ontology that I think, actually we can all talk about this a bit, but the way to support integration while still allowing local curation is Shackle tied to repos. So, GIST isn't really meant to be an application. It's not for ontology. So we've been kind of silent on this for the most part. We haven't been putting very many application hints in GIST. We've been trying to describe what we think the real world is. But obviously, anybody who extends GIST thinks about these things. Eventually, you do have to build a system. So we went through, here's some options of how to deal with optional properties, how to think about it. But I thought maybe I'll turn it over to the floor. What do you guys think about that? What do you guys do when you want an optional property?
Well, Dave, let me ask a slightly different question back. if we accept that shackle would be the thing we ultimately want to get to while you are developing an ontology or extending GIST for your own purposes, would the use of annotations at that point be a good thing to add in, so that later when you do go back to start building out the shackle, you've got a lot of those things already laid in to tell you what you intend? Or do you think you should be developing your shackle and your ontology side by side?
I'm leaning to that. I think the drawback at the moment is the tooling isn't there, but I think it will be pretty soon. And I'm looking forward to a time when I've got two windows open and I'm building my shackle and my ontology in parallel.
Yeah.
Can I comment? Oh, go ahead, whoever that was.
Go ahead, I'll come back.
All right. So one thing about that, Dave and Dan, is are you developing an ontology for a single use for one application? Because if you are, then doing things in parallel makes sense. If you're building an ontology that you hope to be generic across a multiple range of uses, then it doesn't actually make sense to build the shackle at the same time, because it will be application specific.
Right. Yep. Yeah. No. By the time you're building shackle, you're looking at an application. So you hopefully, you've got an upper ontology plus your application extension.
Right. But what I'm questioning, what I'm asking about is you're saying you're leaning towards. Maybe I misunderstood you. Leaning towards developing shackle at the same time you're building the ontology. But that limits that. I don't see why you would do that.
Well, I can add to that, because I've been doing something very similar in the work I've been doing recently, where I might get the basic building blocks in place of the ontology, but usually in our work, at least, there is a first application or a first use case we're thinking of. So I might spend a week or two getting the ontology settled, but then I will start creating check shapes alongside, because as soon as I want to pass it on to someone to use, the check shapes double as great documentation for someone learning to query, or for the data conversion. If a developer converts the data for me, they can see, in something that's maybe a little easier for them to read. Instead of going into Protege, they can, or into our E6 visualization, they can just see, is this there? This is supposed to be there. I must not have written my script correctly, or something like that.
Right.
So usually I start working on the shackle documentation, at least, very shortly after I feel like I've got a good working start to an ontology, because it is helpful for other people to use besides me.
Have you found that the shackle you develop, a lot of it would be true and useful for almost any application for the ontology, or is it really highly application specific?
I think it depends. A lot of what I've been doing lately is all about modeling like system metadata and mapping metadata, so it is pretty specific to the challenges of having users map things together in an application. Go ahead.
Yeah, I was going to say, we haven't had much chance to experiment with this much yet, but what I think is going to happen is we're going to want some tools to move shapes from repo to repo, because sometimes you'll sit down, like in our time card system, if we build a shape for states in the United States, we go, oh, that's not just for us. We could push that, and anybody who wanted to maintain states in their abbreviations or something might want to use this shape. But yeah, right now I'm kind of with Andy. I'm feeling it's kind of application specific primarily, but not entirely.
I think some of it's going to depend on, when it comes to your ontology, how and whether your ontology is really meant to be used for reasoning. Because to a certain extent, just the way I kind of comment things is you mentioned checks before, Dave, that I think the one of the impetuses that led to checks was schematron, which you kind of set in the XML world. You separate out your schema is for validation. This is the vocabulary. Are you using the right words? And then schematron is conformance, And conformist is, are you putting the words in the right way and are you making sense? And so the thing about are you making sense is almost always application dependent, but the way you approach designing an ontology and designing your corresponding shackle files might have a lot to do with are you expecting to run Pellet or any other reasoner in order to, because really the ontology is covering the what is possible and really the meaning of I think of a person as an organic being and blah, blah, blah. But that has nothing to do, as you said before, the ontology is not the right place of saying you must have a social security number. And that's the role of the conformance. And again, the way, if you're not doing any reasoning in your ontology, you're likely to end up with min zeros all over the place, in your ontology, because you're just simply saying this is possible.
Yep.
And my gut feeling is that I think your approach to assigning shackle files to your repositories is probably pretty good. Although I kind of question, and this is a detail as far as at some point you're going to have two different repositories that talk about a person have two different shapes. So how does the application deal with the merging of two different shackle shapes on the same class? I don't know how you do that, but
Right.
But anyways, I think the last piece I was going to say is I suspect, coming back to Michael's question about why would you actually develop your shackle at the same time you're developing your ontology, is if you're developing the ontology as your enterprise view of the world, I think there's also probably a default enterprise view of the constraints. And so you can be thinking through, it's just more of a discipline. You're putting what is in the world in your ontology, and then just your best guess in terms of, I think every person has a, whatever, has a heartbeat. And so you kind of put the constraints into the shackle, and I think that just kind of builds some discipline, even though that enterprise view of the constraints might not actually get used by a runtime application. It comes back to what Andy said about that's documentation.
Yeah, I think the schematron analogy is probably a good one. I don't know it well enough, but what little I know, it sounds like that is a good analogy.
But I think the syntax of Shex, that compact syntax, the non-XML, non-RDF-based syntax that the Shex originally had, was inspired by schematron's compact syntax.
Yeah, cool.
The RNC markup.
Cool. Anybody have any other thoughts? Maybe I'll turn the recording off, and that way if anybody